Okay, hello. Can people online please let me know if you can hear me?
Yes, we can hear you.
Thank you very much. Good morning, everybody. Bonjour. I'm sorry for the late start. As usual, there's always little gremlins that come into play with these sort of hybrid meetings, but thank you very much for your patience. So my name is Greg Sleep, and I'm the session chair for this first session, which is the MWA workshop session for members. So we're going to have three different sections to this session this morning. So first up, we'll have Maureen Rajendran talking about MWA ASVO, which is the MWA's data portal for downloading data, how to access data and use the portal. Then we're going to have a hands-on workshop hosted by Dev Null, and Dev will be taking us through how to process MWA data. So hold on to your hats for that one because it is a live demo, so that will definitely be fun. And the third session is a bit of a Q&A session with the MWA operations and management teams to ask whatever you like, really. And that will take us up to the lunch break. So during this session, please feel free to go out and use the amenities, get a coffee or whatever, because we don't actually have a dedicated break in this session. So without further ado, let's get Urian up here and to talk to us about MWA ASVO.
All right. Yeah, hi, good morning, everyone. Bonjour. This is the first time I'm using this word in real. Yeah. All right, so this is Maureen Rajendran. I'm a software developer, part of software and systems team at Kyra. So today I'm going to give you an overview of MWA ASVO and data access. So in this presentation, I'll just give you what is ASVO, and what are the data you can download from ASVO and Vivo standards supported by MWA ASVO. And I'll give you a little tour of our data portal and how to download and browse through the observations and submit jobs and download jobs, manage your jobs and everything. And finally, with some tips and tricks. Right. So let's get into it. Should I use this too? Thing. Yeah, here it is. No. What do I do? Yeah. So what is ASVO? ASVO stands for All Sky Virtual Observatory. ASVO provides the researchers to access the astronomical data from all the astronomical observatories in Australia. So there are 5 portals under ASVO. MWA is one of them, and the other 4 are TAO, SkyMapper, Data Central, and CASDA. So all these portals follow the Vivo standards to give the interoperability. So the Vivo standards provided by MWA ASVO is TAP service. TAP service is a table access protocol, which gives you, a common way of browse through or find the metadata of the observations you're after. So you can either use TopCat, a Windows application, or PyVivo, a package to find out the metadata of the observations. So if you use TopCat, open your Windows application, go to Vivo, and then you have to enter the URL. For that URL, go to our data portal and then find the URL there. You can copy it, paste it in the URL, and use that service. This will pull all the the tables we host in our Vivo service. You can see all the tables we host. There is a MWA schema and then a table called observation. Under that has all the information is. So you can just write your ADQL query there and run the query to get all the information. Here I just put 2 timestamp, so you get all the observations between that timeline and all the metadata to that. So usually people use OpsCore table to store their metadata in, but we use as different schema MWA and different table, because we want to include more radio astronomy related information as well. Those are not part of Vivo standards yet.
Sorry, there's just people online saying they can't see the slides.
Really? Okay. Do they see my screen instead, or? Oh, they
Yeah,
see
there's no slides.
The data The data captured on site is sent down to POSI through a 100 gig link. So in POSI, we have around 53 petabytes of data archived with 17 petabytes in self storage and 40 petabytes in cap storage. Yes, 53 petabytes is really huge. Just for comparison, you can save 12 plus million Hollywood movies in high definition. And yeah, so ASBO, our data portal just sits in between the researchers and the archive. So we deliver it to two different places. One is Scratch, which is in POSI. POSI is our supercomputing center that provides us all the storage and supercomputing for our data. So we can either deliver there or upload it to Acacia, which is also provided by POSI. It's a S3 interface where we can upload it and give you a signed URL. So you can use that URL to download the data wherever you want. And what are the type of data we provide? So we basically provide two types of data and two on the fly generated. So first one is raw voltages. The raw voltages are the raw data directly from our receivers. 0.781 microsecond time resolution it has. So if you capture that data, it would take 85 terabytes per hour. So this is for MWA expert group. So this requires special permission to get in. And the next one is raw, uncorrected, uncalibrated visibilities. These also the raw data that comes from, but it is bespoke MWA fixed format, and this is also used by expert MWA research groups. And the next one is on the fly, corrected, uncalibrated visibilities. So this one is corrected and pre-processed by our software called Billy. Billy is the software that does the file format and conversion and applies data corrections to the data. So it produces CASA measurement set and UV fits. So this is used by intermediate users. They do calibration themselves. And the next one is on the fly, corrected and calibrated visibilities. So we do apply calibration, but it's very basic but enough for simple quick imaging. This is also used by non-MWA radio astronomers, produces same CASA measurement set and UV fits. Yeah, and all right, so I'll take you through our data portal. So this is our home page where you can see so you can see the outage notice. We always put our outage notice whenever there's a policy maintenance or our website is on maintenance, and we have all the acknowledgements and data collections we have and all the information about them, and the services we provide are in the next tab. So all the web clients and things, and the support. If you need any support or documentation on anything, you can just get here. So it is very well documented, and you don't need anything else. You just go to the support and get the documentation or contact us. We'll provide you, all the support you need. And yeah, to get the data, so you definitely need to register yourself with ASVO, and we accept 2 logins, login provided by Data Central, and another one is our local one. So you just enter your details and credentials there, and click submit, and there will be an email sent to you to confirm your email. Once it is confirmed, we will get an email so that we can activate your account and provide the permissions that you need to access the data. And yeah, just log in with your username and password, username or email, and sign in. And if you have a Data Central account, you can sign in with the Data Central account. And yeah, so you can click on the observations button once you log in to get this page where we have 44 fields that can be searched. So including cone search, you can put time, GPS time, or observation mode, data size, or you can just enter SQL query yourself. And we use the same tab service we provide to the whole world using TopCat or PyVivo package. So you get the same result whether you use a web client or TopCat or whatever the client you use to get the data from the tab service, right? So yeah, it's better if it's a web portal, and you can easily get it with an interface. So we recommend using it to get your observations and details about it. And if you want to get more details about a single observation, you can click on the information symbol left to that, and it gives you all the information of all the channel list and the tiles that were good at that time, and so many other information that I don't understand most of the time. I'm a software developer, not a master. So yeah, yep. So if you want to download, submit a job. So just click on a single observation to get to this page. This is a voltage job, which I show you. This is a raw voltage. It's a huge data set. So we are providing you, a lot of flexibility of downloading a subset of that. You can just enter the offset duration and then the channel you want to download. The channel in the sense that it's a frequency. So one channel is 1.28 megahertz. Of the whole 30.72 megahertz bandwidth. So if you want to suppose download 70 to 80 megahertz with bandwidth worth of data, you can just select the channel 1 to 8 and you get only that data. And the next one is visibility download job. This is also a raw format when you can download with visibilities or only the meta feeds. This is also raw and used by the expert groups. And the next one is conversion job. This is where when you submit the job, you can give parameters like time resolution, frequency resolution, and the edge width, and so many other things. It can be delivered to Acacia Scratch. If you want to do your signs in Posy Scratch system, you can select that. Or if you want to, if you are somewhere else, you don't have a Posy account or a place to use the supercomputing, you can select Acacia to download wherever you want and do your signs there. Yes, and here one thing on the apply calibration there. So that's button. If you click on that, we apply the calibration to your data, and it's a basic calibration again, but it gives you some good results. If you see the one on the left is no calibration applied, and one on the right has a calibration applied. You can clearly see it has good resolution, and it can show you some sources on the sky. So yeah, it's always better to apply the calibration to, if you want to do a basic calibration, and then you can apply your own calibration after that if you want. And there is another way of submitting jobs. You can select multiple jobs in a single go and click on submit download or submit conversion. It's the same page, but at a different it's a model dialog where you can do the same thing and submit the job, or you can export the CSV file. So it creates the CSV file with all the parameters in it, and it's an Excel format. You can use it to use your CLI clients if you're using your CLI clients to download the data, browse through the data. In later point of time, I will go through that too. And yeah, and if you go to your profile and my jobs, you'll see this page with all of your jobs, with all of the statuses, and at the end you can see download links to them. So you can just click on it, and it downloads to your laptop or wherever you are accessing it from. That's how you monitor the job. So we recently added a new feature of resubmitting the job. So if you want to resubmit your job, like you lost your local storage somehow, if you're in Posy, they have a time frame. After that, your data will be erased. So you don't have to do all the things again. You just go to your My Jobs and resubmit the job. The job will be resubmitted. And yeah, we provide two CLI clients. One is MWA client and another one is Giant Squid. MWA client is built in Python and supports 3.8 to 3.10, and Giant Squid is built in Rust and version 1.1.0. And this is advanced. It has advanced features, and we recommend it because we are also planning to grandfather MWA client maybe near future. So we all recommend you to use Giant Squid in future if you are using MWA client. Going on. So to use the CLI client, first of all, you need an API key. So we authenticate your request to ASVO using API key. So still you have to go to the data portal and go to your My Profile. You will see your username and things, and you can get your API key there, copy it, and then export in your local as MWA_ASVO_API_key. And then this key will be used whenever you access MWA ASVO portal. The backend, it authenticates you with this API key. And yeah, of course, get the CSV file of the observations, and then you can use MWA client. So I've given you the README of both the clients. So you can just go there to the GitHub and README, and you can just read through that and install it in your local. It is very well documented, so you can just do it by yourself without a problem, or just contact us if you face any problem. Yeah, and for submitting the jobs, use MWA client -c to pass in the CSV file that we downloaded before and the directory wherever you want, and this will submit the jobs, and it'll wait for it to it'll show the process and things, and it'll wait for it and download. Or if you just want to submit the jobs, you can use different parameters of that MWA client. You can just use help to see. Just use MWA client -help. It will give you all the parameters that you can use with that client. And if you want to monitor the job, you can use -L to the MWA client, and it gives you the status of your jobs. And MWA -D and -W will download the jobs that are ready to your local. So otherwise it will tell you if it is in Scratch, it's on Scratch, so you can just go to Scratch and access the data there. And the next one is Giant Squid. So for Giant Squid, we don't need the CSV file, so you can just pass in the parameters and the ops IDs that you need. So if you want to pass multiple ops IDs, just do it, or on the CLI in interface itself. Otherwise, put all of your observation IDs into a text file and pass the text file to JSquid. It will find out how many observations are there, and it submits that many jobs for each job for one observation. Yeah, so I've given some examples here. You can also always use help to see what are the options you got from JSquid. And yeah, JSquid list your jobs and monitor them, and use download to download the job wherever, download the observations wherever you want. And moving on, so now you have submitted a job, and you might see that some of the jobs have finished really quickly, and some of the jobs are taking too long to finish. It's because we apply a priority index to balance the queue and reduce wait times. So the priority index is indirectly proportional to number of jobs. For example, if two users are submitting, one user is submitting 500 jobs, another user is submitting 100 jobs, the first 100 jobs of both the users will be finished at first, because your job number 1 gets a priority index of 1, and your job number 500 gets a priority index of 500. But the other user gets 1 to 100 because the user submitted only 100 jobs. It is not good for that user to wait for all the 500 jobs to finish and then get his 100 jobs to run. So that, and the voltage jobs are given relatively lower priority due to its long processing time. So but there is a cap for that. So if you are submitting 2000 jobs, for an example, not the 2000th job will not have the job index of 2000, but it is calculated by ASO. Yeah, and yeah, some of the tips on to get the permissions are MWA members get full permission, and there is an embargo on our data. It's 18 months for the non-MWA users. And if you want to access some of the projects, there is a special project permission can be given to you. If you want to access a particular project, you just have to mail us or get the approval from your PI, get your PI to email us that they need access to this. So we can provide you access through our ASBO, so you can access it. And MWA VCS POSI group is needed for accessing VCS data. So it's a little bit longer process. You have to get a POSI account, and then contact us if you want any. You need approval from Steven to get access to this data. And email asbo_support@mwatelescope.org whenever you need support. And expect longer wait times if you if you submit so many number of jobs. And one tip for the voltage jobs is split your voltage job. If you're submitting, for example, if you're submitting a job of 5400 seconds worth of data, we recommend you to split the job and split into 3 and split 1000 seconds each. So it gives you it will be placing your data into 3 different directories, but you can just collect them back, because most of the time you hit the wall time of POSI supercomputing system, so it delays your wait time even more. And these are future plans. So we are currently working on this custom delivery option where right now we deliver only to Scratch. Otherwise, Acacia give a signed URL to you where you can download. We are also working on this custom delivery option where you can just in your profile you can use your API key or something like that, and select your custom delivery option, so we can deliver straight away there, instead of going through a 2 process of downloading the data. And the next one is Astro Query. So we are also planning to work on this Astro Query. So in your Python code, if you're using Python code for your science, you can directly import MWA from Astro Query and then start using MWA.search and get all the metadata and download them straight away in your Python scripts. So soon enough we will be implementing that. And the next one is migration to Setonix. We have been using Garawala for all of our processing. So we will be migrating to Setonix soon enough, and end of this year. And Vivo registry, we are also working on that to list our MWA Vivo service in the registry, and course channel, selecting course channels for conversion visibility jobs. So we have implemented it for voltage jobs. Also currently working on it's in our queue to implement that for visibility and download jobs as well, so that you can always download the subset, whatever the subset you want. And transitioning to Open API, this is one good thing. If you implement this Open API, you will be able to directly use our endpoints in your in your scripts or code straight away, contacting ASVO to do your stuff. And yeah, that's the end of it. Thank you so much.
Thanks very much, Marion. Great talk. So we've got 5 minutes for questions. So Venus is going to be monitoring online questions, and so she will let me know if there are any. So do we want to take any questions from the room right now? Anything at all?
So the code channel based selection for VCF data, this is something recent thing that you have implemented?
Yes, in our last release.
Okay, so that's really a good thing because with the data rates of twice higher, and I think it has been like a bottleneck. The last we do the calculation channel by channel. Very useful.
Exactly, yeah. Yeah, the question was, when did we release this feature of selecting course channel? As it was the last release we did last month.
Just a question.
Yeah, sure.
So the system runs in a regular mode or only runs on a specific place? Because you said the outage are related to quality.
Yes.
Multiple question about the data outage or is it about the service outage?
Well, yeah, it's a two-part. Actually, the one I showed you, the data portal, is hosted in AWS, so that has no problem. So, but when you submit a job, we use POSI Supercomputing Center to access their system to process your data, stage the data, and then run ability to pre-process it and things and upload it to Acacia. Everything depends on POSI. So if they go into maintenance, so we have to put our ASU on maintenance too.
Thanks.
Any other questions?
Excellent. Can everyone thank Marion, please? Next up, we have DevNub giving us a workshop related to processing data.
So it's
So it's going to take a little while, so 5 minutes for Dev to set up. So please feel free to get up, stretch your legs.
Could I ask to dim the room because all my slides are on black?
We will be resuming at 9:45 local time, so that's in 8 minutes from now.
Maybe. Yep, it's a bell mic.
So it's muted at the moment. Yes, flick that the other way.
When my talk starts, yeah, just dim the lights because it's going to be hard to see some of these slides.
Yeah.
This slide will be impossible to see with the lights.
Okay.
Yeah, and even those lights.
Yeah, I asked Stephanie to close the blind.
Yeah.
But with the setup,
How
do we?
So what I'll do, I'll share this. Share. Yeah. Okay, that'll stop this.
Oh, yeah.
So that's fine.
That will get your screen instead.
Right.
Do you need anything from any other laptop to? Is that
I mean-
kind of a guide or?
You know how I downloaded the so it's not sharing anymore. So maybe you need to stop.
Stop it.
here. And
Yeah.
I will, that seems to be working.
Hold it.
on that. Hi, good morning, everyone, and welcome back to part 2 of the first session. Can I just get a confirmation from people online that you can hear me and that you can see Dev's first slide that says how to process MWA visibilities? Excellent, thank you very much for that. We're a little bit behind, so I will just pass over to Dev, who will go through how to process MWA visibility. Dev, over to you.
Thank you, Greg. Bonjour, everyone. Yeah, it's really such an honor to be here to welcome all of the new members into the collaboration. My name is Dev Null. I use they, them pronouns. I'm going to be talking about how to process everything I know about how to process MWA visibilities. As part of the SKA Regional Centre, I've been working with the MWA operations team to develop the Australian MWA EOR Nextflow pipeline. The full pipeline is outside of the scope of this talk, but I've distilled the most important bits for you in this talk. If you want to see all the details, check out Redeemer Nunake's talk tomorrow for the full picture, including all of the quality analysis metrics and everything that makes up that pipeline. I'll also mention that there are many ways of processing MWA visibilities. I've chosen to instruct you on how to use this method. This is a method that is particularly relevant for people who want to process visibilities for EOR science. Many of the steps here may not be necessary for other science use cases. So take some of this stuff with a grain of salt if you're not EOR, and it's up to you, I guess, which steps you decide you want to include. So you may not want to go ahead with the pre-processing stage because that's something that ASVO can do for you if you're not EOR. So let's get on with it. There will be a little bit of awkward switching between multiple devices, unfortunately. Okay, and another thing before we start, on the screen here is a link to the workshop that we are going to be doing today. If you also check your emails for the instructions as well. So what that has is a link to the demo data that you're going to download. Now, it is a lot of data, and this Wi-Fi, if we all downloaded at the same time, just occurred to me that since I'm presenting on WebEx on the same Wi-Fi as everyone else, that might cause issues. So I hope everyone has read the email and downloaded the demo data in advance. If not, maybe you can go through it at a later time. So the other thing is that it will require Docker to be installed, and when you have everything, we have demo data and you have Docker in place, you can run the test script, and that will print out a nice little everything's working message. Hopefully no one has any technical issues with demo, because that's impossible to have any kind of technical issues. So the other thing is part of the demo, I will be skipping over the ASVO component of the demo. We can come back to it if we have time. But that the ASVO component of the demo would require an ASVO account, obviously, and you won't be able to download every single MWA visibility data using an ASVO account unless you have. Maureen has already gone into the details about the proprietary period and all that stuff. And yeah, any feedback that you have is welcome. So I'm just going to move that cursor so you can see the bottom of the screen. Great. Yes. So next slide.
Sorry,
Yep.
they can't see.
Can't see mine. Can't see me, or
Can't see you.
Okay.
So
So this camera is the one that would be seeing me, right? How does that work? How does that go? How's that going online?
I think it should.
Aha! Just click it again. Yep. One more time. Got it. Well done. Okay, you can see me online. Awesome. Woo! One step too far. There we go. So I know there's a lot of new members. Some of you would be very familiar with these details. But yes, so the MWA has another name that is referred to as Gurgumanu. So that's the Wadjuri name, so that for the telescope. So MWA is operated from the Inyaramana Ilgari Bundara, which is the CSIRO Murchison Radio Astronomy Observatory, which is a remote site on the lands of the Wadjuri Yamaji people in the Murchison region of Western Australia. It's also where the SKA low is being constructed at this very moment. So at 27 degrees south of the equator, there's a good view of everything below about 30 degrees of inclination. And MWA can observe 30 megahertz at a given time in the VHF band. So that's, around the 80 to 300 megahertz range. It has a relatively wide field of view with a primary beam full width half max of 25 degrees at 150 megahertz. So one of its greatest strengths is the massive raw data archive that Maureen just talked about, which has been amassing over the decade of operations that we've had. So yeah, all you need to access this archive is an ASVO account. So we're going to talk, before we can get on to how to process things, we kind of need to talk a little bit about the instrument itself. The signal chain specifically that brings you the data. So so we're going to talk a bit about the tiles that collect the electrical signals, with their receivers that digitize those signals, and finally the correlator that takes those digital signals and correlates each pair of antennas. So the MWA is made of tiles of 16 dipoles, which are arranged in a 4x4 pattern in a grid on a mesh. And what we call a tile is what SKA would call a station. It's a tile, the tile connects the dipoles together with a beamformer, and the beamformer is a device that has a selection of delay lines, analog delay lines, that can add a delay to each dipole signal before summing them all together. So unlike maybe the SKA's approach, the beamformers in the MWA, because they're made of analog delay lines, that allows you only a certain discrete grid of pointings that you can steer the tile towards. So the tile is able to point in the direction of a certain number of discrete directions on the sky. When you combine all these 16 dipoles together, that is an effective aperture of about 4.5 meters. We have a series of tests as part of operations that we use to find if there are faults in some of these tiles. So we have a set of tests that we run every day, and these are what we use to find the dipoles. And then if we find a bad dipole, we will disable that dipole. But it's worth noting that disabling dipoles actually changes the primary beam shape. So that's something that you might need to consider when you're calibrating MWA data. It's worth making sure that your calibration software takes into account these dead dipoles or disabled dipoles. So let's talk about some of the configurations that you'll see. So we've got 256 tiles, but only enough receivers to connect 144 tiles together at any given time. Of course, the correlator, the new MWAX correlator, has the capacity to handle many more receivers, and they will be coming along very soon, in 2025 or so. So in order to kind of balance the needs of various different science groups that may require different configurations, we change configurations at the moment between observing seasons. And this, I believe, this might be once we get the additional receivers in, that's going to we're not going to need to change much anymore. But there are two main configurations that we have. The extended configuration in orange is where we have kind of optimized things for maximizing baseline length and getting really nice, smooth UV coverage. And that gives you, with that maximum baseline of 5.3 kilometers, you effectively get about 1.3 arcs second minute, thank you, resolution at 154 megahertz. And then the other configuration that we have is the compact configuration, and this is one that is mainly used by epoch of reionization. I think it's also useful for pulsars as well. So what that has is we're aiming for short baselines, lots of redundancy, and those short baselines are going to be sensitive to more diffuse structure. So what that results in is the effective UV coverage that you get looks like this. And it's hard to get both the compact and extended UV coverage to show up in the same diagram to scale. So what I've done is I've used this projection here. If you don't use the projection on the left, it comes out more like looking like a nice Gaussian, distribution UV coverage. But yes, you can see that the extended configuration has a nice, pretty distributed layout, and the compact configuration is very much going for compact UV coverage. So there are two kinds. There are, as of 2020, there are multiple kinds of receivers that we have in operation. So we'll start with the original. The RRI receivers are as old as the MWA itself, and it really is a testament to the designers that they have survived this long. There are 16 of these receivers. Each of them take 2 polarizations from 8 tiles. Some of the RRI inputs need whitening filters on the longer cable runs. So this might seem like an excessive detail, but it will come up later. So the analog signal goes first through an 80 to 300 megahertz bandpass before being digitized into an 8-bit signal. That signal is channelized into 1.28 megahertz critically sampled coarse channels in the polyphase filter bank. And what this means is we will eventually need to channelize this signal later on. When we channelize this signal later on in the correlator, the channels at the edges of the coarse band are about 6 decibels quieter than the edge, the center channels. So we'll talk a bit about this later. And what happens next is we need to reduce this 16-bit signal down to a 5 real plus 5 complex signal. 5 plus 5 bits. So 5 real, 5 complex. This is, again, it seems like an excessive detail, but we will be talking about a thing called Van Vleck corrections that corrects for some of the artifacts that you might see because of this quantization that happens. So the digital gains are used to basically minimize the effect of this digitization stage and improve the dynamic range. So we choose a digital gain that basically gives us the best, depending on what we're observing, you would choose a digital gain that gives you the best dynamic range. So that's the old receivers. Now onto the new receivers. So we have 16, should be 16 dipole. That's not quite right, sorry about that. We have currently 2 tiles on the NI receiver, and there are plans to put 128 tiles worth of shower receivers. So yeah, we have one type of receiver, the NI receiver, and we have another type of receiver that's coming in very soon, 2025, that will have an additional 128 tiles on those shower receivers. So the shower receivers have a polyphase filter bank that is comparable to the RRI receivers. So there's the digital signal coming out of these receivers is not going to be too different, but each cable, each receiver type, sorry, that should be, has a different sort of flavor that's going to affect what that receiver is going to see. So the thing about the shower receivers and the NR receivers is instead of this should be 4x4 bit quantization, the 8 plus 8 bit, we get 8 plus 8 bit instead. So there's less quantization that's happening in these new receivers. There is all the details of these new receivers we're going to be covered in Jake Jones's talk later on. So now onto the correlator. There is a new correlator that has come online in 2021 that has, so there's a lot of benefits of the new correlator compared to the old correlator. So the new correlator has, instead of, it's a GPU Fourier transform to a finer resolution of 200 Hertz, ultrafine channels. There are a number of new extra features that the new correlator does, like phase and delay corrections. It allows you to do finer resolution, so it goes down to 0.25 second resolution, time resolution, or 200 Hertz channel resolution. But you can't do both at the same time, unfortunately. That would just be an absolutely obscene data rate. So you can choose for precision in time or precision in frequency, and so resolution, I mean. And there is the possibility of doing bridging with SK low. That has, compared to the legacy correlator, where we had 4+4 bit quantization and a resolution of 10 kilohertz and 0.5 seconds was the best resolution that we could do on the old correlator. So yeah, there's a big lot of advantages of the new one. All right, so now we're going to talk about the software that we use to process the data. So what we start off with, we get the raw files that come out of the correlator. They go into a program called Beely. Beely is the preprocessor, and it removes all of the effects that I talked about in the instrument itself, that the instrument imprints on itself, on that data. It also does RFI flagging, which it's best to do this RFI flagging at the finest resolution you can. So before you average the data and convert to a different format, you want to do the RFI flagging at the full resolution, and after that we use a program. We're going to talk about Hyperdrive for calibration that does direction independent calibration. We'll talk about what that is. It also has the ability to do ionospheric subtraction. More on that. And we're going to, part of this demo, we're also going to make a little image using a program called WS Clean. I will note that we have at EPFL, there is a blue build algorithm that seems pretty cool. I didn't get time to integrate that into our demo today, but worth noting that there are multiple ways of doing imaging and calibration. So the folks are here to chat about that later. So then, if you are doing EOR science, you'll also want to do power spectrum estimation. And what I think a complete pipeline does is takes quality analysis metrics from all of these stages and uses those quality analysis metrics to filter out bad data, do flagging, and we will cover a little bit. We'll get a little sample of the quality analysis metrics in this demo as well. So yeah, Beely reads the raw files, does flagging, does various different corrections for the instrument. Those corrections are that we correct for the cable lengths, the lengths of cables between the receivers and the tiles. We correct for the passband shape of the polyphase filter bank for the legacy receivers, and we correct for the nonlinear signal chain corrections that I'll talk about in a sec. And we also do Van Vleck corrections is very soon, nearly finished. It's in a separate branch at the moment, but we're hoping to get that on the main branch soon. Then finally, we average together the channels and time steps to whatever resolution you like if you're reducing the data, and we convert to a different format. So let's talk a little bit about Van Vleck correction. So I talked about the different quantization stages that happen at the legacy correlator and the RRI receiver. The 4+4 bit is the legacy correlator, RRI 5+5 bit. There is a subtle nonlinear effect that we see because of this quantization, especially in observations. So yeah, quite early observations that have a digital gain setting where some of the channels might have been set to a low value. The low values going into the digitization stage is where we see these effects. So in blue, we have the uncorrected autocorrelations of just any particular single antenna, and the orange is the autocorrelations after the correction. So you can see there is a noticeable difference, and this does make a difference if you are further using the autocorrelations to improve your calibration solutions. So again, this is one of those corrections where most science groups won't need to do this. It's something that really the EOR group is, but it is important for EOR science. It is a very expensive correction to make as well. It does take thousands of core hours per time step at 40 kilohertz. So it's not the best. Yeah, it's not an ideal correction for everyone to use. But it does mean that instead of having these little spikes at the coarse channel edges, you get nice, smoother coarse channel. You can see that it is not completely corrected, because what I'm showing here is only showing the correction for the 4+4 bit legacy correlator. The second stage of Van Vleck correction is not fully understood yet, and no one has implemented that correction yet. That is something that would be great to get some help on, because it's very difficult to do. So maybe once we get that correction, we'll see a even flatter spectrum for our autos. So the other thing we get from Van Vleck corrections is actually reduces the false positive rate. The false positive flagging rate. And so I'll show that in the next slide. And I just mentioned that the Van Vleck corrections, so Beely, it's in a separate branch. PyUV data, it's out of the box, ready to go. And there is a Cheboyshev approximation of the correction as well. So you might want to have a look into both of those options. So PyUV data with Cheboyshev approximation and without approximation. You might want to look into whether the approximation is suitable for your science. So I mentioned that it does have an impact on flagging. This is what I mean here. So on the top plot, we have the correction is enabled, and on the bottom plot, we have the correction is not enabled. And then down the bottom, we have in blue, no correction, in orange, correction. And sorry for the, I can just, you can see hopefully online people can see my cursor. You can see down here, we have, when you have the correction enabled, it actually makes the coarse channel edges a little bit thinner. And for these particular channels, this is the same observation as before, right? This is the same observation down here. The higher channels are a lower digital value going into the digitization stage. That actually, this what I've plotted down here is I've taken an observation that has no known RFI, which means that when AO Flagger flags this observation, it is all false positives that we're seeing here. And it's a very small rate. It's like in the 4 or 5% sort of region, but we get more false positives when we don't enable Van Vliet corrections. So just something to keep in mind. Yeah, so AOFlagger is the default flagging program that is built into BLE. It is a very clever algorithm, very efficient, and it is really good at finding certain types of RFI. But we'll probably see, you'll see later in Jade Dushan's talk that there is a lot more other ways of doing flagging and plenty of other types of algorithms that you can use to pick up flags that AOFlagger will not pick up. So yes, but AOFlagger is built into BLE. Yes, and there are other flagging algorithms. So we have SINs as well. Yeah, I will kind of quickly go over this. Yeah, where it's just a completely different approach, where AOFlagger looks at the magnitudes of each baseline and polarization separately. SINs uses these steps to combine all of the baselines together and look at the difference in time between each of the time steps, sum of all of the baselines over the baselines, and yeah, it is able to find RFI that AOFlagger can't find. But it can sometimes, because it's not picking which baselines to flag, if there is RFI that only happens in some baselines but not others, then it will flag everything, all baselines at that time step and frequency channel, unlike AOFlagger, which is really granular. So yeah, and one day it would be fantastic if we could put this put the SINs RFI flagging into BLE, because right now, when you're processing, when you're pre-processing data, you want to be able to apply SINs flags that have been calculated from the raw files or in the raw resolution, but that can't be done after you've averaged the visibilities with BLE. So yeah, there's a lot of talks. There's a lot more details in there. Check out Jade's talk later on. Yeah, just quickly showing some of the stuff you can find in SINs. I don't know what the sources of these are, but if you are quick, you can have a look at that OBS ID there, and you can download this yourself and run SINs using the demo, and see for yourself what's going on in these. They're very interesting signals that SINs has picked up. This has come out of the work we've done with the EOR pipeline. We've gone through 20,000 observations and just made a movie of what SINs, what comes out of SINs, and just found a lot of really interesting stuff. All right. Then we have nonlinear signal chain corrections. So yeah, before 2020, this is not a thing that you would ever need to think about. But now that we have multiple types of receivers, there are some non-linearities that are present that need to be cancelled out. That need to be corrected for if you want to, yeah. So this picture, this plot here shows the receiving correction. So in blue we have the NI receivers with an anti-aliasing filter. In orange we have the RRI receivers with an anti-aliasing filter. In green we have the RRI receivers with a whitening filter. And oh, green's not even showing up. That's probably because it's very similar to the RRI with anti-aliasing. And then we have SHAO with yeah, SHAO. And you can sort of see, yeah, this plot is showing that on x-axis is frequency, and the pink vertical lines are at would be 70 or 80 and 300 megahertz. So it looks a bit weird outside those ranges, but you're not going to be observing in those ranges. So within those ranges, it's, and if you pick a 30 megahertz patch within those ranges, it's relatively flat. But yeah, there are slight phase corrections, so y-axis is the phase. There are slight phase corrections that you would want to do to correct for the difference between these receivers. So the offsets, so these phase offsets that I've plotted here are provided in a metafits file when you download an observation, and very soon we'll have a feature in Billy that will automatically apply these corrections for you. Yeah, so that will be coming soon. Okay, now it's finally time for a demo. So I'm going to swap over to VS Code. Okay, so hopefully all of you have yeah. Of course I can. Thank you. How is that? Is that good? Awesome. Thanks for that. There's a couple of different ways you can run the software in this workshop. I'm going to preview. You can use Docker, which is what I recommend for everyone who hasn't done this before. You can just install everything on your local machine. That will take a while, but you will get the best performance. You can use a hybrid, a mix of the two, or you can even use Singularity if you have a login for an HPC environment. But I'm going to be using the hybrid approach. So I've got some of the stuff installed already, but not all of it. So I'm just going to get this to kind of add some extra paths to run Docker for the stuff that I don't have, and then I'm going to run this to make sure that my path is correctly set. If you're just using Docker, all you need to do is run Docker run. Just copy this from the README. You'll need to pass through your Azure API key, and then what you'll get is a Docker shell. When you're in the Docker shell, you can run the test command. So we go demo test, and that will just check that everything is working. And of course, it didn't find it. So we're going to revert to the Docker installed. Good thing I've got a backup. All right, we're going to run this Docker shell here. And of course, Docker's not running because I just booted this. We tested this demo many times on many different machines before we ran it. So now I'm in a Docker shell, and when I run demo test, it is doing all the tests and making sure that all the software is working. So we see this message here, which means everything is good and we're ready to go. So what that's doing is that's downloading our Beam file, it's downloading our source list, it's validating our source list with Hyperdrive, it's validating our Beam file, it's validating that WSClean is the right version, that all of the Python packages are installed. So we are good to go. The next thing I'll do is the full demo includes a lot of stuff that Maureen has just covered. So I'm just going to skip over the demo stuff. But there is some stuff there on how to use the tap service to do a query and see what observations are available. Hopefully that's still visible. You can look at have a look at that. And there is also a demo that gives you the commands to download all of the observations that you just got from your query. And I should mention, in MWA world, we have this identifier for an observation that is the number of seconds since the GPS epoch was, wherever that was, 19 something. That identifies uniquely each observation. Usually they're about 2 minutes long. And there is another demo in here about how to use the MWA lib library to get information about, yeah, so I will do that actually. So let's say, so you've downloaded, we've skipped ahead and we've downloaded our raw files. And of course, this demo shows that you can download raw files, and it is also possible to download pre-processed files that have been calibrated. So most of this demo is not going to be necessary for you. Cool. Great. We'll skip over that. The raw files appear to not be there, which means I'll just make sure that I've got my raw files in place. That's so strange. I'm going to actually set my OBS ID just to make sure. That is so funny. Okay, we'll skip that. Let's see if we can do the pre-processing demo. Wow, wow. All right, I think there's an issue with the raw files. I think I know how to fix it. All I got to do is uncompress the raw files. So we'll unzip this. Great, and this is going to take about 30 seconds to unzip. It's so strange that happened. There we go. Great. That's our raw files. Good. We'll go export OBS ID equals blah, and then we will run the running the demo. We're going to run the MWA lib demo. I have to go into my Docker shell again, of course. Docker. Yep. Docker. Of course. No, could not have expected the demo to go perfectly. Okay, no, we're good. We're good. Now, running the demo, MWA lib. So, what we have is we have our raw files. Let's pretend we download them from ASVO. We have our metafits files that we can download that come with the raw files. And then what we're going to do is use MWA lib to wow. Maybe the metafits has just been updated or something like that. Well, we'll try the other OBS ID. I wonder if anyone else is having any issues like this, if it's just me or whether it's a global issue. Maybe it's just my setup. That's wow. The amount of times we tested this demo. Okay, well, for some reason the MWA lib demo, some issue with it, not sure. We'll have a look at that and push a fix to the repo later. What we're demonstrating here is we're using the program Beely to take our raw files and convert them to UV-FITS format. There's multiple kinds of formats that we use in astronomy. There's UV-FITS and measurement sets. UV-FITS are a lot more HPC friendly. Measurement sets, we've had all kinds of issues with measurement sets on Lustre file systems. UV-FITS, it's just all one file rather than lots of tiny files. And UV-FITS are also used by the calibration quality analysis software that is demonstrated here. So we have Beely, we've got, it prints out a whole bunch of information about the observations, so the time steps, the channels that have been provided, and it shows you what it's doing. So it's performing cable length corrections, using AO flagger to flag each baseline, and then it writes it out to a UV-FITS file. And yeah, so let's open that demo/05 prep. We have a so if the this is how you provide different things. So you got Beely. These are the flags that we can provide to Beely. We can set the averaging. We can set the edge width, the flagging edge width, and all of those settings. And we also use this program PrepVizQA to look at the RMS values of all of our autocorrelations in our pre-processed visibilities. So that's how we're running it here. And then what that does is in our demo data, 13121. Yeah, 13 prep. It creates these quality analysis files that will, so what we're plotting here is the RMS of all of the autocorrelations that are present in the file. And it does some analysis and picks out the ones that we should be concerned about, that we should be flagging. And so it's circled the ones, the autocorrelations that we should be flagging. And it actually prints out it actually writes all of the information out to a JSON file that you can use for flagging later. So we have the bad antennas field in the JSON. These antennas, it's picked out as being bad and that you should flag these antennas. We'll see what I've done as part of this demo is I've deliberately disabled the flagging because I want to show you what it looks like when you don't flag these antennas. I think it's really important that we automate the flagging to find bad antennas, because not all of the antennas are flagged in every single data set automatically for you. So yeah, then we plot the QA results, and so that's pre-processing. So now we're going to get on to calibration, and I'll go back to the slides to talk about what that means. But first, does anyone have any questions? Greg.
Yeah, I think it would be a good idea to maybe briefly explain the role of the methods file in this, because it's such a central component, and I don't think any of the talks so far have mentioned.
Sorry, Tim, if you can say that again so that it's on the
Yep. Greg's just mentioned that it would be a great idea to talk about what the role of the metafits file is. That is kind of covered in the MWA lib demo, but it is basically an extra file that contains all of the metadata about an observation. And so the important things that you wanted, some of the most important things that you want to get from a metafit file are for the legacy correlative files. It's not really apparent. For the MWAX files, it is pretty easy to see that this file is associated with channel 137, and that's, you know, the center channel of that course channel is 137 times 1.28 megahertz. That's really easy to see with the MWAX file format. With the legacy file format, it is not as easy to see which channel is which. You can see the host name of the correlator that made this file, but the information about what channel is which file is which channel is in the metafits file. And there is a lot of details. Yes. So what this demo does is it extracts that information for you and puts it in a nice little table that prints out like this channel, this GPU box file is associated with this channel, and so on. The other main thing that you're going to get from a metafits file is the information about which antennas are connected to which receivers and their location in space, their the signal chain, other things about the signal chain as well. So I'll quickly grab one of the metafits files and just show you one of the really quick ways that you can inspect a metafits file is by doing fits header on that metafits file, and you get this table. So this is just the header of the table, but this is saying there are two tables in this file, and the first table has information about your antennas, and really it's actually about the inputs, which is like each antenna. And when we say antenna, in this case, in this context, we're talking about a tile. So there is like an antenna number, but it's really, these are like, there are, 2 times the number of tiles of rows in this metafits file. And that is the number of inputs, and that is every tile has an X and a Y input. And then there is information about the cable length, whether that tile is flagged, the receiver number, the polarization, X or Y, the name of the tile, north, east, height, that's the coordinates where the tile is, the digital gains that have been applied for that antenna input, the beamformer temperatures, the delays, the beamformer delays that have been applied for this tile. So that's the each of those numbers is a multiple of some number of microseconds that gives you the delays, that gives you the pointings that that tile is pointing towards. You have the cable flavor, which is the type of cable that connects that tile to a receiver. You have the calibration delays, calibration gains, whether a whitening filter is there, and so on and so on. The second table in the metafits is information, various different bits of information about the observation itself. Also this one here is about the corrections. This is a new table that has been added to do the nonlinear corrections, and it has a 256 numbers. So that's one for every coarse channel. That is basically exactly what I plotted in the signal chain correction slide, but one angle for I believe for every coarse channel. All right. Any questions about metafits? Yep. What I did is I used the program called Fits Header, and that's available in the Docker image. That Fits Header program is a generic program that will print the information about any fits file. But if you, it's really unfortunate that this demo seems to have blown up just now, because this MWA lib demo will print out all of this information, like the channels, the mapping of channels and the mapping of tiles in a CSV file or TSV file that's nicely formatted, and it's really easy to read all that information. That's the point is that these metafits files are a little bit tricky to read. You need a Python script to read them. But the MWA lib Python script here prints out, the receiver number, all the information you care about, the frequencies of the start, center, and end of the channel, the antenna, tiles, all of this information about the tiles, and it prints it out in a CSV file. Has anyone managed to do that part of the demo? Oh, that's great. That's awesome. So it's just my machine that's happened. So I'm glad that the demo is not completely broken. Good. Okay.
Somebody has
Yes.
signed up online.
Hi, can you hear me?
Yep.
Yeah, so I was just curious whether one can also access the raw PPTs from the file, from these tiles in some
That
way.
That is a great question. I haven't talked about PPDs, but that is a question I think I'm going to have to ask you to email. What would be the best email for Andrew to get a hold of Andrew to ask for PPD information? Because Andrew's the PPD expert.
Yeah, I mean, it's andrew.williams@fed.edu. Yeah, if you happen to help.
Yeah. I'll have to get Venus to put that information in the chat for you. Is that okay?
Did you want to explain what PPD is?
That's what I'm going to do now. So this is the MWA web services page that you can access for any observation. So you just put your observation ID in here. And again, this URL, maybe you can get to this URL from the wiki. And I've forgotten exactly the wiki page that tells you how to get to the web services information about an observation, but maybe Greg can put that in the chat. Thanks, Greg. So this web services page is quite there's a lot of information about each observation ID. It's got all the information that is in a metafits. and it has this great beam map. This is what the instrument sees during your observation, and it's in the background we have the Haslam 408 map of the radio sky at 400 megahertz, and we have a couple of bright sources. So this is an EOR observation. This is my favorite EOR observation for some reason, because it has a lot of zeros in it and it's easy to remember the numbers. And what we have is the beam pattern superimposed onto the sky. So you can see that, you know, this is 25-ish degrees across, but we also have the side lobes on the side. And down the bottom, finally, we also have information about which tiles are flagged and all of that. Down the bottom, we have the PPDs. And I think the actual acronym for what PPD stands for has been lost to time. I don't think anyone actually knows what that means. But it is, I believe, I could be wrong about this, it is the power measured at the receiver at the coarse channelizer. So the analog signal has been coarse channelized. It's gone through the, maybe it has gone, no, I'd say, given this plot here, it hasn't gone through the 80 to 300 megahertz passband. Or I'm not gonna say whether or not it has. I don't think anyone knows really what the PPDs are, but they are a power plot at somewhere in the receiver that shows you what power each input has received. Now, does anyone want to say anything about the PPDs? Who knows more about them?
It's the power spectral density.
Power spectral density measured at the output of the PFB. Thank you, Jake. Is that right? Cool.
It's the full band.
Cool. Full band from 0 to 327 megahertz. Thanks, Jake. Jake knows what a PFB is. You should PPD. Sorry, you should ask Jake. Yes. To access the PPDs, they are the way that you access the PPDs is different depending on whether you're looking at an observation that is older than a certain number of years, because the amount of data in the PPDs is quite massive, so we can't store it all in one database. Andrew will have to export that information for you in a format that you can. So basically, talk to Andrew. Andrew can export that for you, and the other place that you can get the PPDs, I believe. No, yeah. Basically, chat to Andrew if you want to get information about the PPDs. Okay. Hope that answers the question.
Is there anything you want me to put in the chat box for you?
Yeah, if you could put Andrew's email in the chat. Andrew Williams. Yeah, thanks. Yeah. Okay. Now we're going to talk about Hyperdrive. We're going to talk about how to calibrate, about calibration and the Hyperdrive program. So there are multiple programs that you can use to calibrate MWA data. We're going to focus on Hyperdrive because it's repeatable and it's Dockerizable, and it works on MWAX correlator observations. Okay. So it is probably it is the best bet for the wide majority of science cases. So what Hyperdrive does really well is direction independent calibration, and it does this on each fine channel individually in parallel. It uses the FEE beam that was made by Martin Sokolowski in 2016, the 2016 beam. Which is, as far as we know, the most accurate MWA beam. And it also takes in, you can provide it with the beam file in an HDF5 format, which is the spherical wave harmonic coefficients. So you can build your own beam if you like, if you think you can make a more accurate beam than that one. The other thing is that it is it doesn't necessarily need to run on GPUs, but if you have a GPU, it runs very, very fast. It runs on NVIDIA GPUs and it runs on HIP GPUs. And we are very close to getting it working on Photonics. There is just some really silly bug that is nothing to do with hyperdrive. It's to do with the compiler tool chain and all that stuff. We will have it working on Photonics soon. It's been a year-long effort to basically rewrite hyperdrive for the HIP GPUs, but it's nearly there. We have a couple of different branches that are working features, but they have not yet been fully tested and enough for me to put them into the main branch. So some of these features, you'll have to check out a different branch from the main branch to be able to access them. So the main one of those features is the ionospheric subtraction, which we'll talk about in a bit. The other thing is there is an additional type of tile for the MWA called the central redundant megatile, and that requires a different type of beam. Obviously, it's instead of being a tile of 16 tiles, it is, you can imagine, four MWA tiles stacked together. So that's, yeah, instead of a 4x4 tile, it's a 16x16 tile. And that's going to have a different beam, and that requires a slightly different beam implementation that is also not in the main branch, but you can check out the develop branch for the analytic beam implementation. We hopefully get these features into main soon. It also works on SKA data. There is a SKA Data Challenge 3 happened last year and involved processing SKA low simulated data. And so there is a couple of modifications that are needed to process SKA data that are in the SCC3 branch. And as well, I talked about the Van Vert correction autocorrelations having an impact on the calibration solutions. This is another feature that is in progress, the autocorrelations branch, to improve the gain solutions of the calibration solutions. So what is calibration anyway? What we do is this is the basic picture of it. We simulate the visibilities that we expect to see on the sky. So what we need a very accurate model of our instrument. We need a model of all the sources in the sky that we expect to see, or as many of them as we can feasibly simulate. Because in reality, it is a huge computation to be able to simulate every single sky model source in our sky. What we do then, once we have our model, is we solve for the corrections that we need to apply to every antenna in order to remove any incidental effects, or to basically get everything to add coherently. So that sounds pretty simple, but it's actually a lot more complicated than that. We barely scratched the surface with direction independent calibration, and there is so much more to calibration that we haven't that has not been fully implemented in hyperdrive yet. Yeah, there's a lot there. So there are lots of different pipelines that handle calibration differently. The notable example is FHD, that has a very different approach to calibration and does a lot of stuff that hyperdrive doesn't do. And yeah, I just no way I could just cover all of this in a 20-minute talk. So I will defer to other talks to talk about those other calibration approaches. Some of the things that we should be wary of when we're calibrating MWA data is that the lower you go, the more of the ionosphere is a problem for you. As you get lower, the ionospheric effects are something that are proportional to lambda squared, the wavelength squared, and you start to see very severe direction-dependent effects that will make calibration a bit of a nightmare. Of course, at these frequencies, we're also in Western Australia. We have digital TV and FM radio. Those sort of around about the 100 megahertz mark that will need to be accounted for when calibrating. You want to make sure that you're flagging everything correctly as you're calibrating. And MWA also has one of its best features is its beautiful wide field of view. that does also introduce a new challenge for calibration in that we need to simulate a lot more sources than other instruments. So we need to simulate a much wider patch of the sky and have good accurate beam models of not just the main lobe, but the side lobes and all the way to the horizon basically is where we can be seeing sources that will impact our calibration. So the other thing is we have a signal chain of many different kinds of receivers and flavors of cables. There are different band passes that need to be corrected individually. Those need to be taken into account. You can't take all of those signal chains and add them and assume that they're homogeneous. You need to consider groups of signal chains when you're doing things like using the autocorrelations to improve calibration solutions. The other thing is that the data rate is quite big, especially as we are adding. We're about to double the number of, nearly double the number of receivers that are going to be correlated at the same time, and we have a massive data rate there. So just doing things on the CPU is not it becomes less feasible as we add more and more receivers. So you want to make sure that you're using efficient algorithms and good hardware that can handle that calibration workload. So direction independent calibration takes all of various different effects that can affect your signal, coming from various different sources. So the beam response, the thermal effects in the amplifiers, they can change over time. The cable reflections in the cables, the properties of the actual environment, like if it's the moisture level, the moisture content of the soil and the temperature can all have various different effects on your signal that would need to be calibrated out. You can have the ionosphere can change over time. All of these effects will change over time, and depending on how accurate you want to be, it changes how regularly you need to calibrate. So this is something you need to be aware of. All of these effects change over time and need to be calibrated out. This is what a calibration solutions look like. You have this is the gain solution, the amplitude. So it's not the phase information, but you'll see that the sort of like bandpass, the corrections that we're correcting out change over frequency. So different channels will receive different amplitude corrections that need to be applied. Those black tiles are tiles that have been flagged out. Each little grid, the x-axis is frequency, the y-axis is the amplitude, and the color is the x and the y. And you'll see tiny little bits of RFI that made it through all of our flagging steps so far. AO flagger and SINs have both been applied to this, and it seems like there is still residual RFI even after all of those steps that does appear in the calibration solution. So the calibration solutions are an incredibly valuable source of quality analysis information as well. So we will demonstrate that in a sec. But first, I'll just quickly talk about like the fact that hyperdrive does ionospheric subtraction, and the algorithm that it uses, the peeling algorithm, is something just could not fit into this talk. But I will show a pretty little video of a ionospheric event that was captured. So each of these vectors is a source's ionospheric offset. So the ionosphere causes it to refract in a particular direction. The color is the direction that source has been refracted in. And this is a model of ionospherically subtracting 8,000 sources for each time step. And when you do that, you get to see these really cool little things happening, little events playing out in the ionosphere that I just find absolutely fascinating. So that is on the peel branch of hyperdrive for you to play around with. But couldn't fit that into the talk, unfortunately. We're just going to do regular DI calibration. So swap over. So We will start that now because it takes a while. So I'm going to open up 05, 06 cal. What we're doing is we're checking our pre-processed files have been available from the last stage, and yes, we grab the QA files from the prep stage, and we use that to apply the bad antennas. We flag out the bad antennas when we're calibrating. Remember that I have deliberately disabled the prep QA stage because I want to get to the image and show you how bad the image looks when you don't do the prep QA. So we'll enable that later and we'll redo the calibration and we'll get to see what the difference is. So when we run hyperdrive, we do multiple calls to hyperdrive. There's two sub-programs. The first one is DI calibrate that takes our pre-processed files. And actually, hyperdrive can take in a set of raw files as well. I just prefer to, it's up to you how you like to do it, but I prefer to do the pre-processing BLE because if you want to redo the calibration stage, the van-flat corrections are so expensive that it's better to just save the pre-processed files on disk so that you can calibrate them later. Sometimes you need to change things in your calibration, so it's just good to pre-process and then calibrate, but it is totally up to you. Hyperdrive will take raw files and do all those steps anyway. So you can just run hyperdrive, DI calibrate, you take your data files, you take your source list, which is your model of your sky, you tell it where to output the files, and if you have a set of tile flags from the prep QA stage, you can also pass that into hyperdrive. So that's what we've run here. We have taken our source list, which contains 338,000 sources. We've picked only 500 sources because I'm just running this on my laptop. But you want to be, depending on your science case, you might want to simulate up to 16,000 sources. Like it's very, very subjective thing that you should think about how many sources is appropriate for your science case. We are calibrating. We're going to ask hyperdrive to generate one time step calibration solution. So we're going to ask it to do one calibration solution for the whole observation. Rather, you can ask it to do every time step if you want. We're going to ask it to because we're passing in one raw file out of the possible 24 course channels. It has been averaged to do 128 channels per course file, and out of this many baselines, we have asked hyperdrive. Well, by default, hyperdrive will cut off any baselines that are longer than 50 lambda, which is 85 meters at this center channel, and we are only going to calibrate on a subset of those baselines. We're going to ignore anything longer than 50 lambda. Wait, maximum? Yeah, that's right. So then we generate our visibilities. We do our DI calibration. We get our channels converging nicely. And we've got, it says that 88% of our channels have calibrated, and that's because the channels on the edge channels, in a previous setting, we've said, you notice how these are all zero, from 0 to 7 and from 125. So these are our edge channels. These are the channels on the edge. We've asked BLE in a previous step to flag all of the edge channels up to, I think it's like 160 kilohertz or something. So only those 88% just means that the edge channels, obviously, because they're flagged, they're not considered. So it looks like it's not fully converged, but it is fully converged. And yeah, so we've written our solutions out. So our solutions, I showed that video before, but our solutions look like this. So we go into the cal folder, And our solutions is a .fits file. The hyperdrive produces a fits file that is the Jones matrix that we need to apply to every antenna and every polarization at every channel. And yeah, it's just a Jones matrix array. And when we plot our solutions, this is what they look like. So this is what the solutions that we've got look like. This is the phase information. And so we have frequency on the x-axis, phase in degrees on the y-axis. And you'll notice one of these little tiles is a little bit different to the rest. That doesn't look good, does it? We'll see that come up later. There can be any number of reasons why a tile just doesn't want to calibrate. Because this tile seemed okay in previous steps, so it seemed like it was all right, but yeah, you can find tiles that have issues and get the calibration stage that don't show up in the pre-processing stage. So it's important to get information from every stage, every little bit of source of information you can get to find the information about the bad tiles. So this is these are nice and linear solutions. So they're they're flat, good linear phases. And the amplitudes, you've seen the amplitude before. It actually, the LBA5 tile is what we're having issues with. So it's nice kind of flat-ish phases. This is one coarse channel as well. They'll look different when you have 30 megahertz all stacked up against each other. Okay, and so we've calibrated, we've plotted our solutions. And we've applied our solutions. That's the next step. Next step is to apply the solutions. We get our fits file and we say, hyperdrive, please apply these solutions and give me a measurement set. So we've applied calibration solutions and we've written out our measurement set. And this is just, instead of a UV fits, a measurement set is just a different way of doing the files. I'm doing a measurement set because that's what WS Clean likes. So that's that calibration. So I didn't explain. We have the DI calibrate that generates our solution files. We have our solutions plot that plots our solutions, and we have a calibration QA step that does looks at the calibration solutions and finds bad antennas. Oh, and I was not meant to do that. I'll just delete this and run it again because I want to show you how bad the image is. Do that again. And now we're just gonna quickly show what the image looks like. This is not made with the demo, unfortunately. This was made by Ben McKinley et al. It is an image of Centaurus A. It is my favorite MWA image that I've ever seen. It is really nice image. It's not something that you can just make just with one WS Clean command. It's something that requires a little bit of post-processing and combining lots and lots of data together. But if you follow the steps in the paper that's McKinley et al. 2022, you can create an image as beautiful as this with the MWA. There is so much detail in this image. It's incredible. So we're just going to do that now. We're going to go demo image. We're going to run WS Clean. I'm going to open this and go send an image. We're just running WS Clean. Where pixel scale is 20 arc seconds. The size of the image in pixels is 2048 pixels. Using the IDG grider. Since I don't have I have a GPU, but it's a Mac GPU, so it's special and doesn't work with WS Clean, so you can't use the IDG GPU. But if you do have a GPU, you could change this to use the hybrid mode to use the GPU for gridding. We're using Briggs what's called robust weighting and multi-scale cleaning, using all these settings. And what that final image looks like if we run Carter. Here, we can open up our demo data. This one, image, and we have our image primary being corrected. And now remember, we deliberately disabled the QA step, so this will look horrible. This looks horrible. There's something wrong with this image. It's you can see like the lobes of Sen-A, and now my laptop is really struggling. So I'm gonna tab away and fix this. You got a quick peek at that. I'm gonna tab away and I'm gonna fix this. QA step. So what we're going to do is we're going to uncomment this. We're going to go back to our README, and then we're going to run this thing to delete the calibration and image stages and redo those stages. I'm just going to close this in case it causes an issue. Then we're going to run the QA step again. I'm going to run all these steps again. I'm running prep, but okay, we need to be in the Docker. I'm going to run this step again. Going to take a few seconds to skipping WS clean. So I need to export obs ID equals this, that. I'm going to remove this. Then we're going to run these steps again. Well, there's something going on there. So instead of doing that correction, you can imagine that correction worked and you got a nice image of WS clean. I'm going to run the demo on the other obs ID. So I'm going to run the whole demo on the other obs ID and just show you an image of what it looks like when you make an image of Sen-A with one course channel and only kind of the bare minimal sort of processing on a laptop. It's still not going to look anywhere near as good as this image looks, but we are going to get hopefully something relatively good, nice and quick, going through the calibration, writing out our calibrated visibilities. I ran this on a supercomputer previously, and turns out the laptop that I've got is actually pretty fast compared to. So I've got a M2 Max, and it's only got 12 cores. I ran this demo on this, I think it was like 40 core, supercomputer, and it took so long. I'm not going to say which one it was, but this is actually pretty fast, pretty good performance, given that it's only using the CPU and not using the GPU. So now we're going to open up Carter, and we're going to open up our demo data. That one, image primary. This is primary being corrected. Image of Centaurus A, and the computer is struggling, but we get a little bit of a nicer looking image, a little bit slightly nicer, and I'll just adjust the render configuration so we can see a little bit more of the kind of diffuse structure on the sides. This one not quite as good, but yeah, I think it was a bit much to expect a good image coming out of this. There's a little. You can see if you integrate a lot more data, you might start to see more of this diffuse structure on the outside. But I think that's good enough for a demo. That's a demo. I'll just quickly talk about QA. We have our instrument is located in a very harsh environment. It's subject to all kinds of creatures coming over and knocking over dipoles like camels and kangaroos, especially. Some of the tiles are in a little camel's dust bed, and the camel likes to roll around and knock over the tiles sometimes. So we need to do all this quality analysis, many steps to make sure we catch all the issues that you could possibly get. Yeah, just quickly one on this is the RFI environment. You'll see various things come in from the horizon. You can also see Starlink. This is a horrible image because it is in the compact configuration, but this is what Starlink looks like when it's flying across. And you can even see the Doppler shift in the spectra of the SINS plot here. So as it's passing over, it's going through. It's going high frequency, and then it goes into a lower frequency at later times in the observation. And we're going to talk more about the quality analysis in Redeem and Anarchy's talk. I think I just demoed that. I just demoed the quality analysis and why it's important to flag your tiles. And talking about, how am I going for time, Greg?
You're going good. So
yep.
What we'll do is just shut
yep.
your talk, and then basically we will open up the Q&A. But before that, I will get you to do something first.
Okay.
So I'll tell you once you finish.
Okie doke. So what I've demoed here is, yeah, that's okay. What I've demoed here is how to do stuff on your laptop. That is not going to scale to if you want to do if you want to reproduce the work that Redeem is going to be talking about, processing hundreds of hours of EOR observations. Can't be done on a laptop, unfortunately. You're going to need to use HPC. And if you're going to use HPC at scale, I've got a couple of tips. Automate everything. Automate your quality analysis. Automate your processing scripts. So you could copy and paste the scripts that I've demoed here and extend them however you like. Please do. Let me know, and maybe even contribute a little PR back to the demo if you find something really cool. Automate your building of your software. HPC environments can change. You can have all of your software dependencies can change in an update, and your software just stops working. You need to automate your build process so that your software is built automatically at any point. And automate your software testing. Make sure that you have rigorous tests for each time a software update happens and all of your software breaks. Test everything rigorously so you don't find out in production. Use modular, reusable components rather than a big, huge monolith. Have little things that do one thing really well. That also means that you can have really long, instead of having a really long job that takes forever to get to the 23-hour mark, and then just in the last stage, a tiny little file is missing, or something that you couldn't have possibly predicted kills it. That is horrible when it happens, and the best way around that is to use granular jobs, that small jobs that do one little thing, and have your error handling built into each stage so that you don't have this cascading effect of losing hundreds of concurrent jobs all dying on the 23-hour mark. The worst. Parameterize stuff. You can't make any assumptions about the dimensions of your data anymore. As we add more and more receivers, we're going to go from the 8,000 baselines to 32,000 baselines. So that's those. You can imagine that the resources required to process an observation with 8,000 baselines is going to be different to the resources that needed to process a 32,000 baseline observation. So parameterize your everything, including your resources that your jobs use. Containers are great. They're really good for repeatability, but if you're targeting a specific CPU microarchitecture, you're not going to be able to necessarily run a container that you built on your laptop and pushed to Docker Hub if your laptop is like an AMD CPU and you're running on an Intel CPU and HPC. So be aware that there are tricks, and this is outside the scope of this talk, but there are tricks to optimize your containers for your specific microarchitecture, and GPU driver versions as well can also bite you. So watch out for that. Thank you. Thanks for all that. Never mind.
Well, thank you.
So,
Yep. Thank you very much, Dev. Yeah, thanks for that really detailed workshop. The thing that I was going to ask you to do is, so obviously there's a lot of content covered and moved pretty fast. So would you be able to go sort of at the 10,000 foot view of if people leave this workshop and want to go back and just grab a bit of MWA to play with, what are the high level steps there? Because obviously we went way down into the details. Could you give us just the 10,000 foot view using defaults? No need to get into sort of EOR complexities or anything like that. I think that would be really good. And then after that, we'll open it up to Q&A, and people can ask questions about the demo or processing or downloading data in general. And then after that, we'll break for lunch at 12.
thank you. The short answer is you can request an observation from ASVO, that has been calibrated with a first pass calibration solution. So obviously not EOR level, but it's good enough for most things. You can request a calibrated observation via ASVO, and the instructions are in the O2 download section there. You can request a calibrated pre-processed observation from ASVO that has basically all of these steps included. Not all of them, obviously not Amblec, all that stuff, not yet. You can request that from ASVO, and that will you can ask it whether you want a UV fits or a measurement set. It will give you a download link that you can use. You can download it directly from the web UI, or you can download it using the Giant Squid client. And that is the easiest way to get processed MWA visibilities without all the extra steps. That's it. Anything else?
And then imaging.
Imaging.
Like, what would I do next?
Next thing is you get your. Should I demo this with the script or run WS Clean basically?
Sure. Or your diagram that you've got on your GitHub page.
Oh yes. Yep. So I'll wait a sec. To show this, but on the GitHub page, we'll open the preview. We've got this nice flow that covers all the steps that are covered in this demo. So tap to get your list of observations. You download it with Giant Squid. Instead of downloading the raw data, all you need to do is download the the measurement set. Make sure you download the measurement set because WS Clean needs a measurement set, not a UV fits. Download a measurement set. Use the steps so you can skip because ASVO will do all of the ASVO will not do SINs, but it will do AO flagger, and it will pre-process your files for you. It will not do the prep QA, and it will not give you calibration QA, but it will apply a first pass calibration solution to give you a calibrated measurement set. That calibrated measurement set can be imaged with WS Clean to give you that image that I was talking about, that I showed before, the Carter, displayed in Carter. That's just a FITS image that is produced with WS Clean or your imaging program of choice. Does that cover everything?
Fantastic.
Cool.
Thanks a lot.
Would have been a lot shorter talk if I'd gone through that, but but then, yeah, I know that I asked a couple of people from EPFL what the appetite is for EOR specific stuff. So I know that there was a lot of stuff there, but it was tailored for specifically the EOR folks. And sorry if everyone else would have put you to sleep, but it's good to know that there are lots of extra corrections that you could possibly be doing if you really felt like it. Cool. Thanks.
Yeah, so thanks for that, Dev. And so if people have questions after this, where can they find you?
dev.null@curtin.edu.au. Yes.
And I think also a whole bunch of us are on the MWA user Slack as well, and we will post the link to that in the chat of the Zoom. All right, in that case, we're now in the final bit of this session, which is just a general Q&A session, unstructured. If you've got questions about MWA data, processing, calibration, the demo, things not related to the demo, this is the right time to ask a question. So we'll take questions from in the room and online. And you have Dev all to yourself to quiz and interrogate. And also myself, I manage the MWA data archive, so I can help with that. We also have Maureen in the room as well, who can answer questions about MWA and ASVO. So yeah, any questions? Yes.
I'm actually a beginner here, so how can I use this image? If I get, let's say, I want to get bugs from the core of state on the time, can I use it?
So the question was how to use the images that WS Clean produces to do analysis.
I can do a live demo of that.
Yeah, like we've got 40 minutes. So.
All right, so I'll share my screen again. I use a program called Carter. A lot of people like to use the much older program DS9, but I think Carter is a lot better. So if every single pixel in this image has a value that is the Janskis per beam, I'm not sure if I can confidently go into what the difference between Janskis and Janskis per beam is, but you can maybe someone else can actually answer that. But as you can see, when I'm moving my pixel across this beam, the image, notice how this value here changes as I'm moving my pixel. So maybe it's hard to see from the screen, but every pixel you can read out this value. Carter also has a feature that lets you look at the profile. Now, so if you have these images are a single, we've taken all of our data and we've only produced an image for one channel image, right? You can instruct WS Clean to create images at every however many channels you want, and you can do a spectral profile if you have that set up. But what we'll do is the XY profile. So you can see what I've got is the X profile at the position where the cursor is. And so this is a plot of, as we go along X, we take the pixel value at each pixel and we plot it. So what we can see from this is at the peak, it's 200 Janskis per beam compared to everything else, which is, it just looks like noise basically. But you can actually see, like, in the lobes of Sene, there's these kind of much slower moving sort of peak.
I want the plots from the core and jumps. So how do I convert jumps to per beam and jump?
Any astronomers want to talk about the difference between Janskis per beam and Janskis?
And it's spread over several pixels, right? So in every pixel I have jumps to per beam. So what do I do?
I'm going to defer to someone else. Chris?
Yes.
Okay, short answer is you just need to integrate over the area of your source. So you can use a source finder to go over the image and find pixels that are above a certain threshold, attempt to fit a Gaussian to that, and that will give you the integrated flux density of the source. One of the other things you can do in Flutter that's quite cool, you can interactively fit Gaussians to your image. So you can drop a little circle or a little Gaussian shape on your point of interest and say, hey, fit a Gaussian to this region, and then give it a
You can take chunks you better beat. So if I sound the Gaussian, it will give me chunks.
Yes,
But even the sense of these loads and
yeah. So yeah, Deb's giving us a little demonstration.
Would you like to
I'm
steer?
I'm not proficient enough in cards to do this on the fly.
Yeah.
I'm going to do this faster, but give me sometimes. So brightness is in Jansky's per beam. It will give you a integrated flux, will give you a deconvolved size of your source and or of your quantity of interest.
even if you put it up, if I integrate over ESF, I get flux and jump.
Exactly, yeah.
And in the frequency band, then I go to the next frequency, then I do the same, and then I get the next spectrum.
Yes, exactly. Few things you could do with it, how to make it different, if you have different images. There's a few other ways to take it a bit further, doing other things with WS Clean. You know, you can output your subband images, make a cube, and look at the spectrum. You can get spectral index directly out of your imaging software of choice, which is usually a fitted spectral index. So it makes all of your cleaning components as a function of your frequencies, and then we'll get some kind of spectrums of that. There's a variety of different ways to do it, but yeah, that's a first order explanation.
And if I chain observations, I can get a light curve.
Yes, if you were to do this, if you were to take a night of MWA observing snapshots, and you know where your source is and create a bunch of images, then yes, you can create a light curve like that. And that's some of the stuff that various people like Natasha Walker have used to look at some of these cool transit sources on different scales. Yeah.
I'll just take a step back on that. The axis for beam is the surface brightness, and there's a certain amount of the beam in each and every. That type of stuff is all recorded in a variety of information in the fixed. And so when Carta or any of these other things is giving the integrated Janskys, it's not just doing the math of integrated Janskys, it's also looking at some of these header values to do the conversion.
So in the header, it's written how what fraction of the beam is in one pixel.
What is written in the header typically is the full width path maximum of the beam major axis and the beam minor axis. Those are typically written in degrees by in degree, and also the header of an image file is typically written how many degrees every pixel is in each dimension. So there's a whole bunch of stuff that's going on behind the scenes. Quick and dirty. If you have a point source, which is probably, if you're into axis about like her, you're interested in a point source. Quick and dirty. A peak pixel, the Janskys per beam, if it's a flow of noise, is the integrated flux. That's sort of what it should be for a quiz.
So I can just skip the therapy.
2 4-point sources, 2 0 order, let's say. Yes. I would not do that for any real scientific analysis, but that's a good way to check that your whatever you're doing to fit the Gaussian, etc., is coming out with the right answer. If it's close to that, or a point source.
I would say for an isolated point source.
Even better. Yeah. Sorry.
So
here like mentioning process, and someone told me that there are live model, some sort of
running around. Yes, this is definitely another question that I couldn't say I could give an answer that works for everyone. Even I couldn't even say which sky model is the best to use for every situation, because there are certain sky models that work better in different parts of the sky, different frequencies, different configurations, that you would just really, it is about trial and error. The one that I've included in this demo here is a really good general purpose all round that covers a lot of the sky and a lot of the different frequencies. That's the first one I would try. There are other alternatives. Yeah, if you go deep in the demo, there's information about where to get more source lists. One of those places is the GleamX catalog. The GleamX pipeline GitHub repository has a bits file. It also is the catalog. There are multiple catalogs you can use, but yeah, a rough minimum is I'd say around 500 sources, and that's really just if you've got me to answer, give you an answer that I'm not going to say I can give you any confidence that's going to work for all situations. It probably won't work when the galactic plane is up. It's actually very challenging to calibrate when the galactic plane is in the beam, even in the side lobes. It can be a real challenge. There is parts of the galactic plane that have been modeled in this catalog. But yes, start with 500 sources, check your calibration solutions, look at your convergence values. I didn't talk about this, but Hyperdrive will spit out in the FITS file a results table that has every channel's convergence value. That is a number around the 1e minus 8, 1e minus 10. So for a good calibration, you want a value of 1e minus 9, 1e minus 10. If you have a value that's lower than the default convergence value is 1e minus, minimum convergent value is 1e minus 8. If it is not any lower than that, then that channel is said to have not been converged and is not a good solution. So that convergent value is effectively, without getting into too much details, is the difference between the model, the simulated model, and the data. And if you're not simulating enough of the sky, you're not simulating enough of the sources or enough of the power in the sky, then your convergence value will not be very good, and you might potentially see some of the channels don't converge enough to give you a solution. So look at the convergence value as you increase the number of sources, and yeah, it might be that one choice of source count works well when you're pointing at a nice bright source, a nice bright calibrator. But then as as you point to a different source or a different part of the sky, that source list doesn't cut it, and you need to simulate more sources or potentially do your own modeling. It's certainly not a solved problem that we can say for every single part of the sky we can calibrate perfectly. Does that answer the question?
Yeah,
Good.
that gives us some comfort. I mean, I should just clarify my question was specifically on the problem we have, the very low end or on the high end, like relatively less used part of channel 203, channel 59.
So Ramesh was just clarifying his question that it was about the low and the high end and how to calibrate those parts. Do you have any specific comments about that?
No, just that different. There are people working on different models suitable for higher and low frequencies. I consult the literature. There are different source lists out there that people have published for. Yeah, so yes, There are people who have published source lists that work on the high frequencies, I know. So consult the literature, I would say, or yes, yeah, that's what I said.
Just before I get to Stephen's question, I'll point out as well that there are a lot of science teams working on MWA data out there with a lot of knowledge and skill and experience in all of this. So there is help out there. Probably if you're new to collaboration or don't really know anyone in those science teams to reach out to, this meeting is a really good opportunity to meet people that are already working with MWA data. If you really get stuck and don't know where to turn, then contact the principal scientists. So we've got both of them in the room today. So we've got Chris Risley and we've got Stefan Machine, and they will point you in the right direction and give you a helping hand. Also, anyone in the ops team you can contact as well. So that's in the room here. It's myself, Dev, and Maureen. And yeah, we'll make sure we get connected up with all the right people and help. And Stephen, question?
No, not really a question. Yeah, if you ask for the 30,000 foot view, I might just take the 100,000 foot view and just reassure everyone that the MWA is an interferometer, like every other interferometer. Dev's taken me through a course of close to every little thing that you need to worry about to address modern radio astronomy's most challenging experiment, which is the EOR. If you want the satisfying experience of making a really nice image of the sky in about 10 minutes, you can just download a 2-minute data set of calibrated visibilities from ASVO. You can pump that through your interferometric weapon of choice, APES, CASA, WS Clean. My weapon of choice is Myriad. You can set the half a dozen parameters of imaging, the standard parameters, and 5 minutes later have quite a nice, not EOR quality, but very nice image of the sky to look at and identify all of your favourite objects. So I think it's just worth pointing that out. If you want to get slightly more complicated and calibrate your own data, to make a really nice calibration, you don't need 500 sources, you need one special source. If you grab a calibration solution from 24 hours ago or 24 hours past your observation date, calibration solutions are very, very, very stable with the MWA. If you use that and just do a single round of self-calibration after a clean, you're making perfectly great images of the sky. Yeah, so I'm a professor. Most of this stuff is therefore way too complicated for me. And plus the sorts of science that I'm interested in don't require the absolute ultimate level of calibration and imaging fidelity. You can make really, really good images really, really simply and really, really quickly. And honestly, for most of the MWA papers that I've published, it is on my laptop, so you can still do it. And I probably recommend that approach for anyone who wants to then step into the world of things like the EOR or other comparable, really, really complicated things. But my advice would be to have a go at keeping it simple. If you've ever looked at VLA data or any experimentric data, MWA data will look very, very similar. So just to come to orbit, really just to make that particular point. So not a question.
Thanks for that clarification, Stephen. I think that's very useful. One of the other things as well, which I'm not really going into much in my talk later this afternoon, but I'll mention it now, is just that one of the goals of the MWA ASVO is to make all this publicly accessible data much easier with a lower barrier to entry than has been in the past. When I first started working on the MWA back in 2016, it was almost like you needed some secret recipe to get access to the data and then secret source and recipes to process the data. And I think a lot of that has been improved over the last few years. And we're always striving to make things easier, especially for beginners and also for non-MWA radio astronomers as well. So the general radio astronomers in the public to be able to grab MWA data, it's already calibrated, stick it through, as Stephen said, your weapon of choice, and pop out an image, and then you can use that with whatever other data you want, your optical data or whatever. So yeah, and we're always open to suggestions as well if there's tutorials or documentation or other things to make things easier. Yeah, please just get in touch. Do we have any questions online?
No questions. I have an announcement to make though.
Okay.
Hi everyone, just a quick announcement to those who haven't got their name badges yet or haven't signed the photo consent form before we break for lunch. I kindly ask you to go to the registration desk to do that, please. Thank you.
All right, last call for any questions. In which case, please thank all of our session speakers for today. It's a lot of hard work to get a live demo going, and Debbie did a really good job, so thanks for that. I know a lot of work went into that. But yeah, please thank our speakers.